How can nothing be faster than light when speed is only relative? You always hear this phrase if you watch something about astrophysics: nothing can move faster than light. But speed is only relative. How can this be true if speed can only be experienced measured relative to something else? I must be four. I've read most of the comments and still can't understand what people are saying. Hey, look on the bright side, I've read about it several different times, studied related stuff, vaguely get what they're trying to say, have a fancy degree. And still it all seems to come down to it just is and doesn't work how any of us think anything would normally work. Maybe that's the only answer for now, it just is from things measured. It's because everyone is just stating the rule, not explaining it. Unfortunately, I'm not sure there is an explainlikeimfive explanation for this. It is wildly unintuitive. I think Science Asylum's videos on YouTube did the best job for me, balancing simplicity without pulling too many punches. Wow, OP. You've asked the very same question that Einstein asked himself to come up with one of the most revolutionary ideas in physics. You are correct that speed is relative. If I'm walking up an escalator at 2 ms and the escalator is moving at 5 ms, then my speed relative to a person standing still at the bottom of the escalator is 7 ms, but to someone else on the escalator who is standing still and waiting patiently for the escalator to transport them to the next floor, my speed is 2 ms. But light travels at the same speed from all perspectives. Say a spaceship is traveling at 90% the speed of light. If I shine a torch from the back of the spaceship to the front and someone on the ground can see through the spaceship's window, then the light from the torch will appear to move at the speed of light to both of us. But the escalator example would suggest that to the person on the ground, it should be traveling at 90% of the speed of light plus the speed of light, that is at 190% of the speed of light. So how can it appear to move at the speed of light to both of us? Well, if the person on the ground is looking through the window and everything in the ship, including not only the beam of light from the torch, but the people inside the ship, is moving in slow motion, then the beam of light can appear to move at the speed of light. Mind-blowing, eh? To solve the paradox, time must be relative. Time inside the ship appears to be slowed down to the person on the ground, and conversely everyone outside the ship looks like they're running around like ants to the people inside. Actually, there's a bit more to it than that, since distances are affected too. But thinking about it like this is a good starting point. This is a brilliant question. It is the question that led to special relativity. Motion is relative. The velocity of an object depends on the velocity of the thing measuring it. Speed of light is not relative. Everything measures speed of light the same. That is the paradox. The universe tells us that is the way it is when we measure it. And we try to explain why. But I believe understanding should start there, not with explanations of space-time. To add to this, anything with mass will never be able to reach the speed of light, c. To see how mind-blowing this is, imagine you're on a train moving at 0.8 c relative to the Earth, and fire a bullet going at 0.8 c. The speed of the bullet relative to the Earth isn't 0.8 c plus 0.8 c equals 1.6 c as we would expect, it's actually 0.98 c. No matter how hard you try, the speed will always be less than c. Edit. I'm absolutely loving the discussions below. Special relativity isn't talked about nearly as much for how mind-bendingly amazing it is. Some questions keep coming up, so I'll incrementally post the answers below. What is c? What does 0.8 c mean? C is a constant that's used to represent the speed that light travels at in a vacuum, which is about 186,000 miles per second. 0.8 c is a speed that's 80% of the speed of light, or about 149,000 miles per second. Where did the 0.98 c number come from? If there is a train that's moving at speed v according to the train station, and you fire a bullet at speed u while aboard the train, where u is according to the train, then intuitively we would expect the speed of the bullet according to the station to be u equals v plus u. But it turns out that just adding the speeds isn't completely accurate to get the true speed, and the error grows as the speeds v and u become closer and closer to the speed of light. The actual formula to get u comes from special relativity and is called the velocity addition formula. The formula has v plus u in the numerator, But there is now something in the denominator that we must divide by to get the true speed. This is a nice calculator if you want to plug in numbers and see what the resulting speed, which we called u, will be. Note that if v and u are both much smaller than c, then the denominator of that formula will be essentially 1, and we'll get back u being approximately v plus u. This means that for adding low speeds, we don't need to worry about the complicated addition formula. Instead of a bullet, what if you fired a laser or flashlight from a moving train? Would the speed of the laser beam be greater than c according to the train station? The extraordinary thing about light is that it always travels exactly at c, when moving in a vacuum, no matter who's doing the measurement and what speed they are moving at. Both you on the train and Alice standing at the train station will measure the laser beam as moving at c. Is mass relative? Back in the day there used to be the concept of relativistic mass, but this isn't used anymore. In modern times, the mass of an object is defined as the measurement you make in the object's own reference frame, in which the object is still. So mass of an object is just a number in kilograms that everyone agrees on regardless of what relative speed they're traveling at. You can measure the mass of something by using a balance or some other instrument while the object is still. Does light have mass? According to the definition of mass above, light does not have mass. This means that photons, which can very roughly be thought of as light particles, also do not have mass. Imagine you're on train A moving at 0.8 c relative to the train station, and train B passes you by that's moving in the opposite direction, are also at speed 0.8 c relative to the train station. What speed do you measure train B moving away from you at relative to you? According to you on train A, the station is moving away from you at 0.8 c. And according to the train station, train B is moving away from you at 0.8 c. Notice that this is exactly the same situation we had before in the original comment with the train bullet, where object 1 is moving at 0.8 c, and object 2 is moving at 0.8 c relative to object 1. In this case, object 1 is the train station itself. Then, the speed you measure train B moving away from you at will again be 0.98 c. Imagine once again that you're on a train moving towards a train station at 0.8 c, relative to the station. Bob, who's standing at the station, fires a bullet at your train at 0.8 c, relative to the station. What speed do you measure the bullet coming towards you at? In your reference frame on the train, Bob is moving towards you at 0.8 c. Bob fires a bullet towards you that's moving at 0.8 c in his frame. This is again the same situation as the original comment, see the last question, where object 1 is moving at 0.8 c, and object 2 is moving at 0.8 c relative to object 1. Object 1 is now Bob. You measure the bullet as coming towards you at 0.98 c. If E equals mc2 and light has no mass, wouldn't that mean light has no energy? I'll attempt to give a rough explanation, but I encourage you to do more research online to get a more thorough answer. It turns out that the famous E equals mc2 formula is only a special case of a general formula called the energy-momentum relation. The general formula lets us calculate the energy of an object that's moving at some speed relative to us. This means that energy itself is relative. If a bullet is fired from a moving train, a person on the train and a person at the train station will measure different values for how much energy the bullet has. You get back E equals mc2 from the general formula if you assume the object isn't moving relative to you, in which case the momentum, called P, of the object will be 0 relative to you. So E equals mc2 is the energy of an object that is measured in a reference frame in which the object is still. But light is always moving at c relative to us, so we need to use the general formula. Plugging in m equals 0 into the general formula, since light has no mass, we get E equals pc. This is the formula for energy of light. We know that light must have energy, so this means P can't be 0. So light has momentum, but it has no mass. The formula that's taught in high school of momentum P equals mv turns out to be a non-relativistic approximation that doesn't work for light. Since light is completely relativistic, you can even think about it this way. The speed of light is really just the speed. It's the default speed of everything. It's just that matter gets in the way and makes things slower. But when all those limitations like matter or external forces or whatever are eliminated, the speed of light, also just called c in equations, is the speed it would go. We used to measure how far one traveled across the seas in leagues and how deep the water was in fathoms. Short side note. 20,000 leagues under the sea does not mean 20,000 leagues below the surface of water, but rather traveling such a distance while submerged. It is approximately circumnavigating the Earth in a sub. Essentially, we had one unit of length for horizontal distance, but another unit of length for vertical distance. But of course they're really the same thing, just different units, so we know we can convert one of them into the other. There are about 3,038.6 fathoms in one league. Let's imagine another scenario where we used km for measuring distances north-south, and miles for measuring east-west. Again, same thing being measured, just in different directions. I face north and now in front of me is km, and to my right is miles. But if I turn some amount, now in front of me is some weird mix of km and miles, and so too to my right. The units mix up a little together according to some trigonometry rules. This, at its heart, is what we mean when we talk about space-time. Meters and seconds measure the exact same thing. Just as meters and inches do, meters and seconds do as well. There's a conversion factor to tell you how many meters are in a second. 299,792,458 is equivalent to 1 second. There's about 1.08 trillion meters in an hour. That's what that number really means. We'll get to why it happens to be the speed of light in a bit. When I lay out my grid of meters and seconds, in all my space dimensions using meters, and my time dimensions using clocks, everything looks fine. A meter is a meter, a second is a second. You stand beside me and you lay out your grid, and you agree with my grid. However, if you are moving relative to me, your motion acts like a rotation. You still see a second as a second, a meter as a meter. I still see them as the same, but when we look at each other's grids, we each see the other person is mixing in a little of the time dimension with the space ones and a little of the space ones in with time. We each appear a bit shorter or flatter along the direction of motion, and we each see the other's clock as running a little bit slower. As we go faster and faster, that disagreement about rulers and clocks becomes more pronounced and leads to other interesting effects, namely ways we have to change how we calculate certain things physically because what we thought to be a good description of things was only valid at low speeds. Here's what ties it all together. We are, all of us, moving through space-time at 1 second per second. That may seem like a tautology or something simple, but think about what it really means if space and time are the same thing. If I am going 1 second per second always, and I want to start going 30 meters per second, I'm going to have to take those 30 meters out of that 1 second per second. I'm going to have to take some of my traveling toward the future in time and turn it into moving through space. The best I could ever possibly hope to do is to convert all of my 1 second per second into 299,792,458 meters second. At which point I've stopped going into the future and am entirely moving through space. There's a bit of a catch here though. Having mass means, for reasons, the closest I can ever do is get arbitrarily close to 299,792,458, but I can never quite get there. If I had precisely no mass, I could do nothing but travel at that speed. Light has no mass. So light always travels at the 299,792,458 ms. So far we only know of two other things we think to be massless. Gravity, if it is particles, then gravitons, is massless, and the particles of the strong force, gluons, are massless. Gluons don't travel very far at all, so we don't often think about this, but gravity, changes in gravity, travels at 299,792,458 ms. Gravitational waves, for example,